Picture a world enveloped in a primordial darkness so absolute that if you were transported there from the ever-present glow of modern cities, it would feel like a tangible void. This was an era devoid of any artificial illumination. No electric bulbs, no neon glow, no light pouring from skyscraper windows. In this world, the night was genuine and profound, a velvety blackness filled with unseen mysteries and subtle sounds, where primeval forests stood untouched by the industrial axe. Above untamed rivers and the first fragile human settlements, the sky was not merely dark. It was a living, trembling canvas of innumerable lights. The stars you would have seen were not the faint, hazy specks we glimpse through today's atmospheric pollution. They were brilliant, sharp diamonds scattered lavishly across the fabric of eternity. The Milky Way wasn't a pale, barely visible smudge, but a luminous, dense river of light, shimmering with nebulae and star clusters. It was so bright that on moonless nights it cast faint spectral shadows upon the ground. Anyone looking up at this breathtaking display, whether driven by a sense of unease or simply resting from the day's toil, would have felt something more than the night's chill on their skin. They would have sensed an overwhelming grandeur and infinity, coupled with a deep, instinctive fear of this incomprehensible vastness. What were those lights? And who had kindled their flames? Were they observers? And if so, were they hostile or benevolent? Could they plummet to the earth? These questions, even if never spoken aloud, must have formed in the minds of people confronted with such a magnificent and mystifying phenomenon. The nocturnal world was already fraught with tangible threats like predators and the cold, and this immense, star-dusted sky seemed an extension of that great and often adversarial mystery of existence. To gaze upward was to be a creature striving to comprehend its place in a reality far grander and more cryptic than its immediate environment. Yet, this primal fear was inevitably intertwined with a sense of wonder and the innate curiosity that defines human nature. Over time, these feelings were joined by a critical need to decipher the basic rhythms of this celestial theater. You see, the immense world above was not chaotic. It operated on its own laws and cycles, and understanding them was fundamental to survival. The most dominant of all celestial bodies, the one without which life itself would be impossible, was the sun. Its triumphant return each morning from the east was a guarantee of warmth, light, and security, dispelling the shadows and anxieties of the night. For early humanity, the sun was far more than a simple astronomical object. It was revered as a deity, the ultimate giver of life and source of all energy. Its daily procession across the sky, from dawn until dusk, established the most crucial and obvious rhythm governing all activity. You could estimate the remaining daylight for hunting, gathering, or relocating by the sun's position, which also signaled when to retreat to the safety of a cave or shelter. Its setting heralded the onset of danger and cold, a time to huddle around a fire, preserving a small piece of the day's light and warmth, prompting the very first myths about where it journeyed through the night. Once the sun vanished, another magnificent celestial body took its place, not as searingly bright or hot, but equally significant and enigmatic. To ancient observers, the Earth's nocturnal companion, the moon, revealed itself in a continuous state of transformation. It would first appear as a slender, faint crescent, low in the western sky just after sunset, seemingly born from the darkness itself. Night after night, it would wax, filling with light to become a half-disk, and then a full, brilliant orb that bathed the world in its cool, silvery radiance, making the nights brighter and safer for movement or work. This lunar cycle, from the new moon to the full moon and back again, was so regular and its duration so relatively short, about a month, that it naturally captured attention. The phases of the moon likely served as one of the first methods for measuring time beyond the simple span of a day. People could count time in moons, saying, 3 moons have passed since the great herds were here, marking humanity's earliest effort to structure time. Its undeniable influence on the night and, for coastal peoples, on the tides, was linked to powerful magic, the feminine principle, and the cycles of birth and death. All of this, the sun's majestic daily march, the moon's mysterious changes, and the shimmering canopy of stars, amounted to more than just a stunning spectacle or inspiration for myth. Observing the heavens was born from a stark, practical necessity. In a world that lacked maps, compasses, or any kind of signage, the ability to orient yourself was a matter of life and death. You had to know how to navigate to rich hunting grounds and, just as importantly, how to find your way back to your tribe and shelter after a long journey. During the day, the sun was your guide, its position indicating the cardinal directions. By night, that essential role was fulfilled by the stars. Despite the fact that stars might look as though they are scattered randomly, a sharp-eyed observer would have noticed that certain configurations remained fixed, night after night, and year after year. The very first clues began to emerge as bright stars or stellar groupings that could be committed to memory and used as navigational points in the heavens. By recognizing that one prominent star hardly moved and was always positioned to the north, which you know as the North Star, although its exact alignment with the celestial pole has shifted over time due to precession, people discovered a dependable compass for the night. Other star formations, which rose in the east and set in the west much like the sun and moon, also proved to be useful guides for figuring out your direction or gauging the time of night. Of equal importance was another challenge, forecasting the transition of the seasons. For tribes of hunter-gatherers, understanding when the cold would bring a scarcity of food and when warmth would return with abundance was a matter of sheer survival. When could you anticipate the migration of animals? When would specific fruits or roots be ready for harvest? Or when would the rainy or dry seasons commence? The answers to these vital questions were inscribed in the sky. Ancient people observed that the sun not only journeyed across the sky each day, but also altered its path over the course of the year. In winter, its arc was low on the horizon, making the days brief and cold, while the exact points of sunrise and sunset also shifted from day to day. An even more trustworthy indicator for these early observers was the changing appearance of the night sky itself. Particular stars, or clusters of them, what you would later call constellations, became visible just before dawn or right after sunset only during specific times of the year. The emergence of a familiar star pattern in the morning could serve as a clear signal. The deer herds will arrive soon, or it is time to gather the wild grains, or you must prepare for the long winter. This was not science in the way you and I understand it today. Rather, it was an intuitive and hard-earned body of knowledge that was handed down through the generations. The sky was humanity's first great book, written in characters of fire, and the first clock and calendar that nature ever offered. To look at the heavens was not merely to indulge your curiosity. It was to read the signs that were essential for the survival of your tribe, your family, and yourself. This marked the start of our long journey to comprehend the cosmos, a journey that began with a simple glance upward, filled with wonder, fear, and pressing need. This initial awe, combined with practical necessity, is what first compelled ancient people to study the night sky. However, simple observation soon evolved into an active effort to understand. The The human brain is wired in a peculiar way. It resists chaos. Your mind instinctively searches for order, for patterns, and for familiar shapes, even in places where they might not truly exist. The same mental process that allows you to see figures in the clouds or a face in the texture of tree bark was operating at full capacity when our ancestors gazed into the stellar chaos above. Over time, thousands of glimmering dots, seemingly thrown at random across a vast black canvas, started to coalesce into something more meaningful. This transformation didn't happen in an instant. It was a slow, collective act of creativity that unfolded over millennia, passed from one generation to the next, through spoken word. People began to see that certain groups of bright stars formed outlines that were easy to remember. A line of a few stars might look like a warrior's belt, the curve of a bow, or a string of beads. A denser grouping of stars might suggest the form of a familiar creature, a powerful bull, a fast-moving deer, a cunning scorpion, or a great bear roaming her celestial territory. Other clusters were linked to people, heroes, gods, beautiful women, or formidable hunters. Sometimes they took the shape of objects, such as a ladle, a throne, a plow, or a boat. In this way, from scattered points of light, the human imagination began to weave its first celestial tapestry, projecting familiar earthly figures onto the heavens. This was far more than simple entertainment or a flight of fancy. The act of creating these celestial pictures, these constellations, served as a powerful memorization technique. While it is impossible to remember the positions of thousands of individual stars, you can quite easily recall a dozen or so figures that are tied to recognizable images and stories. Constellations became a way of organizing information about the sky, allowing people to remember where key stars were located and to pass this knowledge down. An elder could tell a young hunter, "When the tail of the celestial scorpion grazes the horizon at dusk, the rainy season is about to begin." Or, "Maintain your path so that the dragon's head is always on your right." Without these mental images and the names attached to them, sharing such crucial information would have been incredibly difficult. But crafting the images was only the beginning. The next, equally vital step was to enrich these figures with meaning and narrative, turning the sky into an immense, illustrated volume of myths. Every constellation, every hero or beast in the heavens, wasn't just hanging in a void. Each was a character in a grand cosmic story. The myths that people shared around their fires on long nights were projected directly onto the stars, which became eternal monuments to gods, heroes, their great deeds, and their tragedies. The sky itself transformed into a stage where the dramas of creation, love, betrayal, conflict, and immortality were constantly performed. For instance, in many cultures of the Northern Hemisphere, a distinct pattern of 7 stars, which you know as the Big Dipper, was seen by the ancient Greeks as part of the larger constellation of Ursa Major, the Great Bear. According to one myth, the beautiful nymph Callisto, who was loved by Zeus, was turned into a bear by the jealous goddess Hera. To protect her from his vengeful wife and from hunters, including her own son Arcas, who became the constellation Boötes, Zeus placed Callisto in the sky. He set her son beside her, and along with the Little Dipper, or Ursa Minor, they watch over the bears, who never dip below the horizon, at least in the mid-latitudes of the Northern Hemisphere, because Hera forbade them from ever bathing in the ocean's waters. This particular story did more than just account for the patterns of stars you see. It recounted the dramas of the gods, touching on themes of love, jealousy, redemption,
and eternal remembrance. When people looked up at Ursa Major, they were reminded of this specific myth, and the stars were elevated from simple points of light to characters in a magnificent celestial play.
Another powerful example is the constellation Orion, the formidable hunter, who is instantly recognizable by the 3 stars forming his belt. According to Greek legend, Orion was a hunter of such skill that he arrogantly claimed he could slay every beast on earth. In response to his hubris, the goddess Gaia, or in some tellings, Artemis, sent a scorpion to deliver a fatal sting. The gods, feeling pity for the great hunter, placed him among the stars, but they also placed the scorpion there to commemorate its deed, ensuring the two would never share the sky. As Scorpio ascends in the east, Orion is already descending in the west, forever escaping his celestial foe. Close to Orion in the night sky, you can spot the constellations Canis Major, which contains the brilliant star Sirius, and Canis Minor, representing his loyal hunting hounds. These myths were far more than simple stories. They served as a comprehensive framework for explaining the world, its structure, natural events, the origins of humanity and animals, and even moral codes. The heavens themselves became a sacred manuscript where the most vital truths and legends were inscribed, with star patterns acting as reminders of ancestors, cultural heroes, and the very foundations of the cosmos.
The act of storytelling linked to these constellations was a fundamental component of education, the passing down of traditions, and the reinforcement of social cohesion within a tribe or community. However, it's crucial for you to understand that the sky was not perceived uniformly by everyone. Different cultures, inhabiting various parts of the globe with distinct landscapes, wildlife, and belief systems, perceived entirely different figures in the heavens, even when observing the same stellar groups.
The Big Dipper, for instance, was seen by the ancient Egyptians as the leg of a bull, a symbol of strength and might. In Scandinavia, it represented Odin's wagon, and for certain Native American tribes it was, in fact, a bear being pursued by 3 hunters, who were the stars of the Dipper's handle. This cultural variety in celestial cartography is the most compelling evidence that constellations are not objectively real formations in 3-dimensional space. The stars that make up a constellation are frequently separated by immense distances and have no physical connection to one another. They are instead a reflection of human culture, imagination, and life experience projected onto the dome of the sky. Each civilization effectively painted its own unique map of the world, complete with its own mythology and symbols, across the heavens. What one culture saw as a hero, another might interpret as a ship, while a third might see it as merely a part of the celestial river we call the Milky Way. Beyond their mythological and memory-aiding roles, a deep understanding of the constellations held enormous practical value, a legacy from the earliest observations that predated these myths. The constellations functioned as dependable navigational aids. In the northern hemisphere, the North Star was indispensable, the only prominent star that maintains an almost fixed position throughout the night and the year, reliably indicating true north. By learning to locate it, often using other constellations like the Big Dipper as guides, travelers, sailors, and nomads could navigate after dark with the same assurance they had from the sun during the day. The positioning of other constellations relative to the horizon and the cardinal points also helped in telling the time at night. Because the Earth rotates, constellations, much like the sun, rise in the east, reach their zenith, and then set in the west. A seasoned observer could, by noting the location of familiar constellations, accurately gauge how much time had passed since sunset, or how long remained until dawn. Even more critically, constellations were used as a seasonal calendar. As the Earth orbits the sun, The appearance of the starry sky shifts over the course of the year. Constellations visible on a summer night are hidden by the sun's glare in winter, and the reverse is also true. The first annual appearance of a star just before sunrise, known as its heliacal rising, or its final disappearance in the evening twilight, acted as a trustworthy indicator of seasonal change. For the ancient Egyptians, the heliacal rising of Sirius, the most luminous star in Canis Major, signaled the imminent flooding of the Nile, an event upon which their entire civilization depended. For farmers elsewhere, the rising or setting of specific constellations could signal the proper time for planting or harvesting. Therefore, the night sky, decorated with the patterns of constellations and rich with mythical tales, was much more than a beautiful spectacle for ancient peoples. It was simultaneously a map, a clock, a calendar, a holy text, and a practical guide for living. These star patterns helped humanity to impose order on the universe, to find its place within it, to synchronize life with the grand cosmic cycles, and to transmit accumulated knowledge and wisdom to the next generation. The creation of constellations and myths marked a pivotal transition from passive observation to the active exploration of the surrounding world. As this knowledge of celestial cycles grew, passed down through the myths and legends associated with the constellations, ancient people began to feel a need to anchor this information, to make it more dependable and less reliant on the fallibility of human memory. They required landmarks and reference points, not just imagined on the celestial sphere, but also physically established here on Earth. This led to people in various parts of the world acting independently, beginning to construct monumental stone structures known as megaliths. These enormous stones, some weighing tens or even hundreds of tons, were quarried with astounding effort, moved over great distances, and arranged in precise alignments, becoming the silent keepers of time, the first man-made observatories, and the physical manifestation of accumulated astronomical wisdom. To this day, these stone titans continue to stand, inspiring both awe and bewilderment. You have to wonder how ancient peoples, lacking metal tools, cranes, or precise instruments, could have erected such monuments. More importantly, what drove them to undertake such a colossal task? The answer seems to lie in a deep-seated human desire to understand and bring order to their world, creating a harmony between life on Earth and the movements of the heavens. Without question, the most renowned of these ancient stone complexes is Stonehenge, situated on England's Salisbury Plain. For centuries, its massive sarsen stones, arranged in concentric circles and horseshoe patterns, along with the solitary heelstone, have captured the imagination, though its complete purpose remains a topic of ongoing discussion. What is undeniable, however, is its profound connection to astronomical events, with the monument's primary axis being perfectly aligned with the sunrise on the summer solstice, the year's longest day. Try to envision the scene at dawn, after the shortest night of the year. The first rays of the rising sun slice through a precisely engineered gap between the stones, striking the central altar, or illuminating the very heart of the complex. For the people who constructed Stonehenge, this was certainly an event of immense importance, possibly their most significant annual festival. It symbolized the absolute peak of the sun's power, the height of summer, and a time of maximum fertility and vitality. Yet, Stonehenge's purpose extended beyond marking the summer solstice. Its architecture also appears to account for the sunset on the winter solstice, the shortest day and longest night of the year. This moment served as a crucial turning point, when the sun, after seemingly dying,
would begin its rebirth. As the days started to grow longer, it signaled a renewed hope for spring and new life, suggesting that this was a time for rituals connected to ancestor veneration, the renewal of life forces, and prayers for prosperity. Given its complex design, Stonehenge likely served to mark other celestial events as well, perhaps related to the moon's cycles, or even the prediction of eclipses, though these latter ideas are more contested. Equally impressive, though constructed in an entirely different manner, is Newgrange in Ireland, a colossal mound that predates not only Stonehenge, but also the Egyptian pyramids. It is far more than a mere pile of earth. It is a sophisticated engineering marvel, with a long passage leading to an inner, cross-shaped chamber.
Remarkably, a small, specially crafted window is positioned above the entrance to the passage. Just once a year, for a few days around the winter solstice dawn, a beam from the rising sun penetrates this opening. It then travels along the entire 20-meter corridor to illuminate the floor of the central chamber for a period of 15 to 20 minutes. This breathtaking display must have made a profound and lasting impression on ancient observers. The symbolism of this light penetrating the core of the earthen mound, a tomb representing the world of the ancestors, was powerful. It represented the triumph of life over death, of light over darkness, and the rebirth of both the sun and the natural world after the dormancy of winter. This was a potent, sacred act that affirmed the connection between the realm of the living, the realm of the dead, and the unending cycle of the cosmos. Stonehenge and Newgrange are simply the most famous examples of a widespread practice. You can find megalithic structures with clear celestial orientations throughout Europe and other parts of the world. In Carnac, France, rows of thousands of upright stones, known as menhirs, stretch for kilometers, which many researchers believe functioned as a gigantic astronomical tool for observing the risings and settings of the sun and moon. In Germany, the Goseck Circle, dating to around 5000 BCE, was built with gaps in its wooden palisades that precisely indicate the points of sunrise and sunset during the winter solstice, demonstrating a universal ancient drive to link life with celestial cycles through architecture. You should not imagine ancient priests equipped with telescopes and slide rules. Their method was based on long, patient observations passed down through many generations. People noticed how the point of sunrise on the horizon shifts daily, migrating from a southernmost point in winter to a northernmost point in summer, and back again. By charting these patterns against distinctive landmarks, a hill, a tree, or a natural notch, they could then position massive stones or build corridors that pointed directly to these key solar events. The moon's movements, while more complex, are also cyclical, and tracking them required not so much advanced calculations as meticulousness, keen observation, and immense patience. Just imagine the task of situating a multi-ton stone so that on a specific day of the year, its shadow falls on another stone, or a ray of light passes through a narrow gap. This was not the result of a single year's work, but the culmination of collective experience, possibly gathered over decades or even centuries. So why did people invest such enormous effort and resources into these grand constructions? One of the primary motivations was undoubtedly practical necessity tied to agriculture. For agrarian societies, knowing the precise times for sowing and harvesting was vital, and the solstices and equinoxes served as the key milestones in their annual calendar. However, to reduce the purpose of these structures to farming alone would be a vast oversimplification. They were almost certainly powerful and important centers for ritual and ceremony as well. This new time frame offered a much closer match to the actual rhythm of the seasons,
prompting the rise of solar calendars centered on the sun's annual cycle. Among the most renowned and effective of these early systems was the ancient Egyptian calendar. You see, life in Egypt was completely tethered to the Nile River and its yearly floods, which deposited fertile silt upon the fields, making the prediction of this event absolutely critical. Egyptian priest astronomers observed a remarkable pattern: the reappearance of Sirius, the sky's brightest star, known to them as Sothis, in the pre-dawn hours after a lengthy absence, heralded the Nile's impending flood. This event, the heliacal rising of Sirius, became the foundational reference point for their entire calendar. The year was structured into 3 seasons of 4 months each, their names reflecting the agricultural cycle: Akhet, the season of inundation; Peret, the time of growth as the waters fell and planting began; and Shemu, the period of drought and harvesting. Because 12 months of 30 days only added up to 360 days, falling short of the year's actual 365-day length, the Egyptians appended 5 extra days at the year's end. These were known as the epigomenal days. They were treated as a festive period, dedicated to the deities Osiris, Horus, Set, Isis, and Nephthys, and existed outside of any specific month. This calendar system provided far greater seasonal stability than its lunar predecessors.
While a count of 365 days is remarkably close to the true duration of a solar year, the Egyptians were aware, or at least eventually discovered, that the year is longer by approximately a quarter of a day. This is the same 6-hour discrepancy we now correct with a leap year. However, they never incorporated leap days into their civil calendar. As a result, their calendar year fell slightly behind the solar year, causing the heliacal rising of Sirius to drift through the dates, completing a full circuit in roughly 1,460 years, a phenomenon known as the Sothic cycle. Despite this astronomical drift, the Egyptian calendar proved sufficiently accurate and practical for the daily needs of several generations. The inherent difficulty in harmonizing lunar months with the solar year also gave rise to a different system, the lunisolar calendar. This represented an effort to retain the familiar lunar months, while still keeping them synchronized with the solar year and its seasons. The challenge was considerable, figuring out how to accommodate about 12 1/4 lunar cycles within a single solar year. The solution they devised was intercalation, which involved periodically inserting an extra 13th month into the year, resulting in a calendar that had either 12 or 13 months depending on the year. Determining when and how often to add this intercalary month required much more sophisticated observations and calculations. It became essential to monitor both the phases of the moon and the sun's position through events like equinoxes or solstices to prevent the calendar from drifting too far from the seasons. Prominent examples of these complex lunisolar systems include the Babylonian calendar, which heavily influenced other cultures in the Middle East, along with the traditional calendars of China, India, and the Jewish people. Though more intricate than purely lunar or solar models, these calendars masterfully aligned the lunar phases, crucial for rituals and daily affairs, with the annual cycle of agriculture. Thus, you can see that creating a calendar was far more than a technical exercise in timekeeping. The calendar evolved into a powerful instrument for structuring the entirety of ancient societal life. It dictated not only the schedule for agricultural tasks, but also the timing of religious festivals and ceremonies that were woven into every aspect of human existence. The calendar governed when taxes were collected, when military campaigns were launched, when fairs and market days were held, and when civic and religious obligations were due. It synchronized the lives of individuals and communities, establishing a shared rhythm for their existence. Mastery over the calendar, the ability to maintain and interpret it,
was frequently a privilege reserved for priests or rulers, which in turn reinforced their power and authority. The calendar was not merely a sequence of days, it was a framework cast upon the flow of time itself. It allowed people to bring order to the chaos of existence, to plan for the future, and to connect the present to the past through repeating cycles of celebrations and significant events. By capturing time, measuring it, and dividing it into segments, humanity took another monumental step toward mastering the world and understanding its place within it. This was a move from simply observing celestial rhythms to actively using them to build civilization. When you retrace this journey in your mind, a path that stretches across millennia, you see how humanity's gaze toward the sky transformed from one of simple wonder and fear into something more focused and purposeful. Our distant ancestors progressed from merely watching the twinkling lights and feeling a primal fear of the vast cosmos to a more deliberate process. They learned not just to look, but to differentiate, remember, and systematize what they saw. They wove recognizable star patterns into constellations of animals, gods, and heroes, using the threads of their imagination and cultural experiences. These celestial figures served as memory aids and also formed the basis of grand mythological systems that explain the very structure of the universe. Simultaneously, a practical understanding of celestial rhythms was developing. The movement of the sun, the changing phases of the moon, and the predictable rising and setting of certain stars became reliable markers for time and direction. What were once incomprehensible celestial events transformed into dependable tools, shaping the foundation of society and navigation. The sky became a sacred text, its fiery letters spelling out the legends of their ancestors and the will of their gods. From the earliest times, people looked to the sky as a natural clock and calendar, using it to anticipate the cycle of day and night, the turning of the seasons, and the ideal moments for hunting, planting, and harvesting. To preserve this crucial knowledge, they erected grand stone monuments, megalithic structures that served as silent observatories, with their internal passages and alignments precisely aimed at the rising and setting points of the sun and moon, marking the most significant times of the year. The drive to structure daily life around the great cosmic cycles ultimately led to the invention of the first calendars, which were based on lunar, solar, or a combination of both patterns. These systems evolved beyond simple methods for tracking days to become the very framework that organized the social, economic, and religious activities of ancient cultures. This entire body of knowledge and practice, which we now group under the term ancient astronomy, was the culmination of countless generations of shared experience, observation, and relentless human curiosity beneath the vast, primordial sky. Of course, it would be inaccurate to label these early observations and mythological frameworks as science in the way you and I understand the term today. They were missing key elements like critical analysis, the experimental testing of hypotheses, and modern mathematical modeling. In their worldview, myth and reality were inextricably linked, while ritual and observation were woven into a single fabric of understanding the cosmos. Explanations for what happened in the heavens were not sought in the yet undiscovered laws of physics, but rather in the actions of gods and the influence of supernatural forces. The celestial stage was seen as the arena for an eternal conflict between light and darkness, order and chaos. Yet, it was this enormous collection of accumulated observations, even when dressed in mythological or ritualistic clothing, that created the fertile ground from which the shoots of scientific astronomy would eventually sprout. Unaware of their future importance, ancient observers were gathering priceless data for the researchers who would follow them. For thousands of years, people tracked the sun's unceasing journey along the ecliptic, the moon's intricate patterns, the rising and setting of prominent stars, and the perplexing, looping paths of the wandering stars we know as planets. The civilizations of the ancient Near East, particularly Babylon, played a pivotal role in this slow transition from myth to a more systematic, pre-scientific approach to observation. Driven primarily by astrological motives, the desire to interpret the destinies of kings, nations, and individuals from celestial signs, Babylonian priests and astronomers maintained meticulous records of their observations over many centuries. They calculated the orbital periods of the moon and the naked-eye planets, Mercury, Venus, Mars, Jupiter, and Saturn, with a precision that was remarkable for their era. They also learned to forecast lunar eclipses and, with somewhat less accuracy, solar eclipses, recognizing their cyclical nature without possessing a correct physical explanation for why they occurred. Their clay tablets, inscribed with cuneiform script, have preserved for us an immense repository of empirical information, detailing planetary positions, the precise timing of eclipses, and the first annual appearances of stars at dawn. Although this data was collected largely for divination and the creation of horoscopes, it became the essential raw material, the empirical bedrock, that enabled the next great leap in our comprehension of the universe. This transformative step was ultimately taken in ancient Greece. Starting around the 6th century before the Common Era, Greek philosophers and scientists took the astronomical knowledge gathered by the Babylonians and Egyptians and approached it with an entirely new intellectual mindset. Their main objective was not simply to predict cosmic events, but to find a rational, logical explanation for the structure of the cosmos itself, to build a coherent, geometric and physical model of reality. They were the first to move beyond asking when and start asking why. The philosophers of the Pythagorean school, captivated by the elegance of numbers and music, proposed that the universe was founded on mathematical principles. They introduced the revolutionary concept of a spherical Earth, suggesting it rotated at the center of a harmoniously ordered cosmos, enclosed by transparent spheres that carried the planets, the sun, the moon, and the stars in a perfect celestial rhythm known as the music of the spheres. Later, Plato and Aristotle formulated more intricate and physically grounded geocentric systems, placing a stationary Earth at the center, surrounded by multiple nested spheres, rotating at various speeds to account for the observable motions of celestial objects. Despite being incorrect from our modern perspective, this model stood as the first complete scientific worldview and held sway over European science for almost 2,000 years. Greek astronomers, leveraging both Babylonian records and their own precise observations, made a series of groundbreaking discoveries. Hipparchus, for instance, created the first comprehensive star catalog, which detailed the coordinates and brightness of over 850 stars. He also determined the lengths of the solar year and the lunar month with astonishing accuracy, and identified the phenomenon of precession, the slow wobble of Earth's axis that causes a gradual shift in the apparent positions of the stars and the timing of the equinoxes. More than anyone before them, the Greeks systematically applied geometry and trigonometry to describe the movements of celestial bodies, to construct cosmological models, and to estimate the size of the Earth and its distances to the moon and sun. It was Aristarchus of Samos who famously attempted these measurements and, incidentally, was the first to put forward a heliocentric model, though his contemporaries did not embrace his idea. Although their ultimate conclusions about the universe's structure turned out to be flawed, their method was nothing short of revolutionary. the search for natural causes, the use of mathematics to describe nature, and the creation of logically consistent models based on observation, laid the very foundation of science. The scientific method in astronomy first emerged in an age of antiquity. Ancient myths and careful observations supplied the raw materials for this new understanding. The Babylonians were instrumental in systematically compiling and preserving enormous amounts of this celestial information, while the Greeks took on the task of constructing the first great structure of scientific cosmology, establishing its architectural rules. Remarkably, the same primal impulse to gaze at the heavens, the profound curiosity that led early humans to lift their eyes toward the unreachable stars, has persisted through millennia. This very drive is alive in you and me, fueling the engine of modern science. Of course, our capabilities have expanded beyond measure. We now operate enormous telescopes on the ground and in space that can capture radiation from every part of the electromagnetic spectrum, letting us look into the most remote areas of the observable universe to see stars being born and galaxies dying. Our spacecraft now journey throughout the solar system, touching down on other planets and sending back breathtaking images and invaluable data to Earth. We have intricate physical theories, including general relativity and quantum mechanics, which enable us to create models of the universe's development from the Big Bang to today. The knowledge we have of the cosmos, its sheer size, its composition, its timeline, and its governing laws, is far beyond what ancient priests and astrologers could have ever imagined. Yet, at the core of all this scientific and technological achievement resides the same basic human yearning to comprehend the world, to find our place within this immense universe. We are still trying to answer the age-old questions that have always haunted humanity. What is our origin? What is the structure of everything? What does the future hold for us? And are we the only ones here? Consider that a contemporary astrophysicist sifting through data from the cosmic microwave background, the residual warmth from the universe's earliest moments, or an astrobiologist designing ways to find life on distant exoplanets, is, in truth, the direct successor to those first anonymous skywatchers who sought to decode the night's mysteries by the light of a fading fire. While the instruments, the cognitive approaches, and the sheer quantity of information have transformed, the underlying motivation has not. That insatiable curiosity about the cosmos, that inherent human need to connect with the great mystery of existence and push the frontiers of what is known, remains unchanged. You and I still look up at the stars, not to schedule our harvests or divine our futures, but with the same profound awe at their cold, timeless beauty and the staggering scale of the universe. This is why, when you study the history of astronomy, it is so vital to acknowledge its ancient origins, which extend thousands of years into the past to a time when the sky was a source of fear, an object of devotion, and an essential tool for survival. You must realize that modern science, for all its sophistication, did not simply appear from nothing. It emerged slowly, painstakingly crystallizing over millennia from countless observations, daring hypotheses, mythological interpretations, and the first desperate efforts to impose order on time and space using the heavens. Ancient astronomy should not be dismissed as a mere catalogue of charming errors or the naive superstitions of our ancestors. Instead, it stands as a powerful monument to the strength of the human spirit, its natural gift for inquiry, and its unending powerful attraction to the stars. By understanding how our forebears first looked skyward with purpose, and how they formed their first cosmic maps in their minds, myths, and monuments, you can better appreciate the magnificent intellectual journey our species has taken. This journey reveals an unbroken chain of curiosity connecting you, a person of the 21st century, with those who gazed upon the same stars thousands of years ago, but perceived them in a completely different way. Their ultimate legacy isn't just specific astronomical facts or impressive surviving structures, but rather that unyielding passion to understand the universe. It is this same passion that propels science toward new frontiers today, promising even more incredible horizons of discovery.
Your universe is composed of billions of galaxies, each one filled with countless stars and planets, all existing within the sphere that our current technology permits us to see. But what might exist beyond that horizon? Let us venture on an exploration past the limits of the observable universe, beginning with a clear understanding of what that term means, its dimensions, its scale, and the boundaries of what we can currently perceive. We will investigate theories that offer clues about what lies beyond, such as the concept of the multiverse, string theory, and the possibility of life on other worlds. Our journey will examine the enigma of dark matter and dark energy, which constitute most of our universe yet are almost entirely invisible to us. We will also consider the potential for parallel universes and other dimensions, which would fundamentally alter your understanding of space, time, and your own place within it all. Prepare to push the limits of what you know as we confront the single greatest mystery of our era. What exists beyond the edge of the observable universe? The phrase observable universe is itself a concept that inspires both fascination and wonder. It represents the entirety of everything you can potentially see or measure from our vantage point on Earth, using our most sophisticated instruments. This boundary is determined by the most distant cosmic points from which light has had enough time to travel to us since the universe began, approximately 13.8 billion years ago. You shouldn't mistake the universe's age for its size. It's not simply 13.8 billion light-years in diameter. Because of cosmic expansion, the estimated breadth of the universe is actually around 93 billion light-years. This immense volume contains every galaxy, star, and celestial body we can currently detect, and our perception of it is governed by a fundamental constant, the speed of light in a vacuum, which is fixed at 299,246 kilometers per second. Consequently, this universal speed limit means that when you gaze at a star thousands of light-years away, you're actually seeing its appearance from millennia ago, as that's how long its light has traveled to get to you. Every observation of the cosmos is essentially a look back in time. Our cosmic horizon is not fixed. It continually grows as light from ever more remote regions finally arrives. Yet the universe's accelerated expansion creates a boundary beyond which some regions are receding so fast their light will never reach us. The force propelling this expansion is a mysterious phenomenon known as dark energy, which constitutes about 68% of the universe's total energy and actively counteracts gravity's pull. To study this expanding cosmos, scientists rely on advanced telescopes that perceive more than just visible light. They also capture radio waves, infrared radiation, and X-rays. This multi-wavelength approach uncovers hidden cosmic features, most notably the cosmic microwave background, often called relic radiation, which is a faint afterglow from the universe's earliest stages, holding vital clues about its initial development. When you consider the composition of the observable universe, it's a truly captivating subject. The cosmos is predominantly empty space, with galaxies like our own Milky Way dispersed throughout like islands in a boundless ocean. Each of these galaxies holds a staggering quantity of stars, and experts project that the total number of stars in the observable universe surpasses the number of sand grains on every beach on Earth, a comparison that highlights its almost incomprehensible scale. Determining the scale of the observable universe is a challenge intertwined with its age just as much as its immense distances, and scientists have devised several ingenious methods to unravel these cosmic puzzles. At the core of this endeavor is the light year, a unit representing the distance light covers in a single year, approximately 9.46 trillion kilometers. This measurement acts as a fundamental cosmic ruler, enabling astronomers to chart the vastness of space. Among the most vital instruments in an astronomer's toolkit are Type 1a supernovae. Because these spectacular stellar explosions always have a consistent peak luminosity, they function as standard candles, which allows scientists to gauge their distance based on their apparent brightness from Earth. By also measuring redshift, the phenomenon where light stretches to longer, redder wavelengths as it crosses the expanding universe, astronomers can calculate the rate of this expansion and thereby approximate the universe's overall size. The cosmic microwave background radiation, that faint afterglow from the universe's infancy, serves as another cornerstone for these measurements. This relic radiation gives us a snapshot of the cosmos as it was only 380,000 years after the Big Bang. By analyzing its remarkable uniformity and subtle temperature fluctuations, scientists can deduce the universe's geometry and expansion rate, which, when fed into complex cosmic models, yield our current estimates of its observable extent. Our ability to perform these measurements has been dramatically improved by technological progress. Modern telescopes, both on the ground and in orbit, are engineered to capture light across the entire electromagnetic spectrum, from radio waves to gamma rays, which deepens our insight into cosmic distances. Furthermore, scientists refine these calculations by applying Einstein's theory of relativity, which describes the universe's structure. For instance, the effect of gravitational lensing, where gravity bends light, enables astronomers to weigh galaxy clusters and thereby measure vast distances across the cosmos. Past the limits of what we can currently observe, there exists a realm of profound cosmic enigmas and theoretical possibilities. These inaccessible regions hold the potential answers to some of the most fundamental questions about the universe's nature and its ultimate destiny. Cosmologists theorize that far beyond our cosmic horizon, other galaxies and stars exist, and perhaps even domains where the fundamental laws and constants of physics are radically different from our own. This leads to the captivating idea of the multiverse, a hypothesis proposing that our universe is just one among a potentially infinite number of others, each with its own distinct properties. In this grander cosmic arrangement, every universe could operate under unique physical laws, contain different forms of matter, and host alternate realities, fundamentally challenging our very conception of existence. Back within our own cosmos, dark matter and dark energy represent two of the most profound puzzles in modern cosmology, continuing to elude scientific explanation. We can infer their existence through their gravitational influences and the accelerating expansion of space, yet their fundamental nature remains a secret. Unlocking the true properties of these mysterious components could completely revolutionize how we understand the universe's structure and dynamics. Finally, we are left with another compelling question that concerns the ultimate shape and scope of the universe itself. Does it stretch on infinitely? Does it curve back upon itself in some higher dimension? Or is there a definitive boundary at its edge, beyond which lies something entirely unknown? Countless theories exist about the unobservable universe, yet they are all conjectural since we lack any means to see these domains directly. This raises fascinating questions, sparking both scientific inquiry and philosophical discussion about life beyond our cosmic horizon. If you consider that life-supporting planets might be common within the universe we can see, imagine the sheer variety of existence that could flourish under entirely different physical rules, pushing astrobiology into a realm of profound speculation about our own place in the cosmos. Looking at the cosmic microwave background, which is the afterglow of the Big Bang, provides you with a window into the universe's infancy and clues about what exists past our sight. Subtle variations within this ancient light could be imprints left by events or structures in the regions we cannot observe, subtly shaping the cosmos we know. It leads physicists to consider that the fundamental laws and constants of nature might not be uniform everywhere, potentially leading to exotic elements or forces that would fundamentally challenge our current foundation of physics, the Standard Model. Although the Standard Model is incredibly successful at describing the particles and forces you see in the observable universe, it is known to be incomplete, hinting at undiscovered phenomena. As an example, string theory speculates that reality includes extra dimensions beyond the three of space and one of time that we experience. In these hidden dimensions, entirely new particles and forces could be at play, affecting our universe in ways that are currently beyond our grasp. Consider the perplexing nature of dark matter and dark energy, which together are thought to make up about 95% of the universe's total mass energy, yet remain complete enigmas. The very existence of these mysterious components strongly implies that there are unknown forces or substances operating beyond our current comprehension. These phenomena serve as a powerful indication that our grasp of gravity and other fundamental forces is partial at best, pointing toward a new realm of physics that awaits discovery. Beyond the edge of what you can observe, in the vast, unexplored regions of the cosmos, scientists propose the existence of theoretical particles that we cannot yet detect or fully understand. These hypothetical building blocks of reality are conceived to fill the gaps in the Standard Model of physics. They not only ignite our imagination, but also propel the ongoing quest for a unified theory that can explain the entire universe. Among the most compelling of these theoretical particles are the candidates for dark matter, like weakly interacting massive particles, or WIMPs, and axions. WIMPs are thought to constitute a large part of the universe's mass, and because they barely interact with normal matter, their presence is inferred only through their gravitational pull on galaxies. In contrast, axions are theorized to be much lighter particles that could solve a complex issue in quantum chromodynamics known as the strong CP problem, while also potentially being a component of dark matter. A separate class of hypothetical particles emerges from supersymmetry, a theory suggesting that for every particle you know from the Standard Model, a corresponding partner particle exists. These superpartners, such as neutralinos and gravitinos, would possess different spin characteristics and are also considered prime candidates for dark matter. The larger ambition of supersymmetry is to unify the Standard Model with general relativity, paving the way for a potential grand unified theory of all physical laws. String theory offers a different perspective, proposing that every particle is just a different vibrational pattern of a tiny fundamental string, which could account for all known particles and forces, while suggesting countless others remain undiscovered. Pushing this idea of fundamental components even further, some theories speculate about particles called preons, which would be the subcomponents of the quarks and leptons you currently consider elementary. Should preons exist, they would unveil a completely new, more foundational layer to the structure of all matter in the universe. Superstring theory radically reshapes our vision of the universe's architecture, pushing your conceptual boundaries far past the observable cosmos. The central idea of this theory is that the ultimate ingredients of reality are not dimensionless points, but minuscule, oscillating strings of energy. A particle's specific properties, like its mass and charge, are simply determined by the unique way its underlying string vibrates, a concept that fundamentally alters how you must think about space and time themselves.
This framework introduces extra spatial dimensions beyond the three we navigate and the single dimension of time. Though it might sound like something from fiction, the theory proposes these additional dimensions are curled up so tightly into the fabric of reality that they are far too small for us to detect with current technology. The consequences of this idea for comprehending the universe beyond what we can see are truly immense. Superstring theory suggests that on the most fundamental level, the universe is elegantly unified, with every force and particle originating from the same basic components, vibrating strings. This concept of unity provides a promising pathway to connect the disparate worlds of quantum mechanics and general relativity. It offers you a tantalizing vision of a theory of everything, a single, comprehensive framework capable of explaining every physical process in the cosmos. Moreover, these proposed extra dimensions could completely transform how you understand cosmic events. It's possible that within these hidden realms, particles and forces interact in ways that are entirely invisible from our three-dimensional viewpoint. This could be the key to finally solving the persistent mysteries of dark matter and dark energy, along with other puzzles that currently defy our standard scientific models. Ultimately, you are left with one of the most profound and challenging questions in all of cosmology. Is the universe infinite? The possibility of a limitless cosmos suggests not only an endless expanse of space filled with innumerable stars and galaxies, but could also mean the existence of parallel realities, including infinite variations of our own corner of the universe. This idea presents a profound challenge, not just to our scientific models of the cosmos, but also to our philosophical and existential beliefs. It posits a reality that extends far beyond the limits of the observable universe, which is the cosmic sphere from which light has had sufficient time to reach us since the Big Bang. This observable region, spanning a diameter of approximately 93 billion light-years, becomes an almost insignificant fragment within the staggering scale of a truly infinite expanse.
The consequences for both cosmology and fundamental physics are immense. In an infinite space, you might logically assume that all cosmic structures and phenomena repeat endlessly, which suggests the existence of a boundless number of planets like Earth, and, by extension, countless potential forms of life. This concept of infinity also provokes compelling questions regarding the distribution of all matter and energy, given that on the largest scales, the universe seems to be uniform and looks the same from every vantage point.
This principle of a limitless universe suggests that large-scale structures, such as galaxies and the clusters they form, are replicated over and over across the cosmos. Yet, the very notion of infinity struggles to align with the frameworks of contemporary physical theories. For instance, a universe containing an infinite quantity of energy would directly contradict our understanding of the laws of conservation and thermodynamics, while the idea of countless exact duplicates of our world, each with tiny variations, raises deep philosophical questions about what makes you unique. From a purely practical perspective,
The hypothesis of an infinite cosmos complicates the work of cosmologists immensely. If the universe truly has no end, it confirms that we can only ever witness a finite sliver of it, constrained by the universal speed limit of light and the finite age of the cosmos itself. This inherent limitation means that a complete understanding of the universe's true scale, structure, and ultimate destiny will likely remain forever beyond our observational grasp, as immense regions are destined to stay unseen.
The theory of cosmic inflation, first put forward by physicist Alan Guth in the 1980s, describes a period of explosive expansion just moments after the Big Bang, opening up a universe rich with possibility. This model proposes that during the first tiny fractions of a second, the universe grew at an exponential rate. This not only elegantly explains the remarkable uniformity of the cosmic microwave background radiation, the faint afterglow of the Big Bang, but also implies that a vast cosmos of structures and phenomena exists well beyond the horizon of what we can currently observe. One of the most compelling concepts to arise from inflationary theory involves the behavior of quantum fluctuations in the early universe. It suggests that microscopic quantum variations were stretched to astronomical proportions by the rapid expansion, seeding the formation of the large-scale structures like galaxies and galaxy clusters that we see today. This process may have also produced vast cosmic domains, where the fundamental constants of nature, or even the laws of physics themselves, are entirely different, creating a magnificent and diverse cosmic tapestry. Another fascinating, though speculative, consequence of cosmic inflation is the potential formation of pocket universes, existing as separate realities within a grander multiverse. Each of these pocket universes could harbor its own unique physical properties, including different fundamental forces, an assortment of elementary particles, and distinct physical laws. This idea dramatically reframes our perception of reality, proposing that our universe is merely one bubble in a vast cosmic foam of countless others, each with its own defining characteristics.
Cosmic inflation may have also facilitated the creation of primordial black holes, which were not formed from collapsing stars, but from immense gravitational pressures during the universe's initial, rapid expansion. These ancient black holes, possibly scattered throughout the regions beyond our observable sphere, could hold the key to understanding the mystery of dark matter. Furthermore, the theory predicts the existence of gravitational waves, ripples in the fabric of space-time, generated by this explosive growth, which could offer us a direct window into the universe's first moments.
The idea of bubble universes offers a breathtaking vision of a cosmos composed of innumerable, self-contained realities, each existing within its own distinct domain. This concept originates from the inflationary model, which suggests that as space-time stretched in the moments after the Big Bang, it could have spawned countless separate universes inside a sprawling cosmic multiverse. These other universes might be profoundly different from our own, featuring their own unique physical laws, fundamental particles, and cosmic architectures. The birth of these bubble universes is thought to be rooted in the inflationary field that powered the early universe's exponential growth. As this field fluctuated, certain areas would have stopped inflating and cooled, creating stable pockets where a universe like ours could form and evolve. All the while, the space between these pockets would continue its relentless expansion, ensuring that each bubble universe remains forever isolated within an ever-growing multiverse. The specific contents and properties of these other bubble universes remain a subject of intense theoretical exploration. It is conceivable that the fundamental forces of nature that govern our reality, gravity, electromagnetism, and the strong and weak nuclear forces, could be drastically different elsewhere. Such variations could give rise to entirely new kinds of chemistry,
or even forms of matter and energy that are completely unimaginable from our limited cosmic perspective. The composition of these other universes could vary dramatically, from nearly empty voids with scarce galaxies and stars to realms densely packed with celestial bodies. This diversity would be determined by their specific rates of expansion and the fundamental physical laws that operate within them. Consequently, the concept of bubble universes presents compelling scenarios for the development of galaxies, stars, and perhaps even life, especially in universes with finely tuned physical constants that foster complexity.
In some of these universes, the conditions might be perfectly suited for the rise of intricate structures, including living beings. However, in others, where these fundamental constants are radically different, the formation of any recognizable structures, let alone life as you know it, could be entirely impossible. Because these bubble universes exist beyond the edge of our observable cosmos, their direct detection is currently far beyond our technological reach.
Nevertheless, scientists propose that we might uncover indirect proof of their existence. This evidence could manifest as gravitational waves, or as specific anomalies within the cosmic microwave background radiation, the residual glow from the Big Bang. Such disturbances could signify past interactions between our universe and others existing within the broader multiverse. Dark matter, an enigmatic substance that does not interact with light, is instrumental in sculpting the cosmos, with its influence reaching far past the visible universe. It constitutes roughly 27% of the universe's total mass energy, and we infer its existence from its gravitational impact on visible matter, on radiation, and on the universe's large-scale structure. Despite being invisible and elusive, dark matter functions as a kind of cosmic cement, binding galaxies together and facilitating the formation of the immense, web-like patterns that characterize the cosmos beyond our observational limits. It is thought that dark matter continues to serve as the principal architect of cosmic structure, with its gravitational influence being essential for the creation of galaxies and galaxy clusters, even in the regions you cannot see. Theoretical models indicate that dark matter's distribution in these unobservable domains likely mirrors what we see within our cosmic horizon, creating a complex cosmic web of dark matter filaments. These filaments provide the underlying framework upon which visible matter gathers to form galaxies, stretching across immense distances that lie beyond our view. Beyond our horizon, dark matter might also be responsible for structures that appear alien or vastly different from those familiar to you. Based on how the density and arrangement of dark matter varies, these distant regions could contain unique galactic formations, or even astronomical objects that are rare or entirely absent in the observable universe. The interplay between dark matter and dark energy, the mysterious force accelerating cosmic expansion, adds another layer of complexity to how these distant structures evolve. Investigating the behavior of dark matter beyond the observable universe could yield vital clues about its fundamental identity. Current theories put forward several candidates, such as weakly interacting massive particles, or WIMPs, as well as axions and sterile neutrinos. By modeling and observing the universe's structure, both within and beyond our sight, we can rigorously test these theories and gain deeper insights into the properties of dark matter particles.
As you contemplate the universe beyond the observable, you might also consider the possibility of variations, or even unknown types of dark energy. These could be affecting cosmic expansion in ways we don't yet grasp. Although dark energy seems consistent everywhere we look, its characteristics could change beyond our field of view, creating regions where expansion accelerates differently, or where its influence fluctuates in strength.
This potential for variation raises profound questions about the true nature of dark energy. Could it be a cosmological constant, an intrinsic property of space-time itself, as Einstein once theorized? Or is dark energy a dynamic field that shifts across time and space, similar to dark matter but with a repulsive gravitational force instead of an attractive one? Theoretical frameworks, such as quintessence, propose that dark energy may arise from a field whose density is not uniform, which could produce observable effects in the cosmic microwave background or the arrangement of galaxy clusters. While direct proof of other universes remains unattainable, some theoretical models provide methods for inferring the multiverse's existence. One potential sign could be discovered by analyzing the cosmic microwave background, or CMB, which is the remnant radiation from the Big Bang. Though the CMB appears mostly uniform, it has subtle temperature fluctuations, and some inflationary theories suggest these could be shaped by encounters with other universes. Therefore, if certain anomalies in the CMB, like cold spots, defy explanation by standard models, they could indicate collisions with other bubble universes. Another line of inquiry focuses on the constants of nature, like the gravitational constant, which seem perfectly calibrated to permit life, a puzzle often addressed by the anthropic principle. In a multiverse, each universe could possess different values for these constants, making our set just one of many possibilities. Discovering that these constants are not uniform across space-time would lend support to the multiverse hypothesis, as would the search for dark flow, large-scale galactic movements that cannot be explained by visible matter.
Some scientists propose that a phenomenon known as dark flow could be the gravitational influence of adjacent universes pulling on our own. Should this be proven, these cosmic patterns would offer compelling, albeit indirect, evidence for realities existing beyond what we know. Quantum mechanics presents an alternative viewpoint, especially through the many worlds interpretation, which theorizes that every potential quantum outcome unfolds within its own distinct branching universe. While this idea currently serves more as a philosophical framework for quantum mechanics than as direct proof of a multiverse, our growing comprehension of quantum phenomena may soon provide new methods for deducing the existence of these parallel realities.
The search for imprints of other universes could yield results from experiments in high-energy physics, like those performed at particle accelerators, such as the Large Hadron Collider, or LHC. Any discovery of miniature black holes, or the observation of particles and forces that defy the standard model of particle physics, could signal some form of interaction with, or influence from, these other cosmic domains. This idea that different universes might be governed by entirely separate sets of physical laws is both an exhilarating and a perplexing notion, fundamentally questioning our conception of reality. Within this multiverse framework, every individual universe could possess a unique configuration of physical constants and principles, creating cosmic settings that are profoundly different from ours. This variance in physical laws might express itself in fascinating and substantial ways, completely transforming the fundamental properties of matter, energy, space, and time from one universe to the next. In our own cosmos, the four fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, are precisely balanced to permit the formation of atoms, molecules, stars, and galaxies. In a different universe, however, a more powerful gravitational force might result in stars that are significantly smaller and have much shorter lifespans, whereas a weaker gravity could prevent the formation of galaxies altogether. Likewise, any changes to the electromagnetic force would impact the interactions of charged particles and the creation of chemical bonds, which would dramatically reshape the chemical landscape and the very possibility of life as you understand it. The fundamental masses of elementary particles, including electrons and quarks,
represent another variable that could be altered in a universe where these particles possess significantly different properties. Such a change could redefine atomic structures, thereby influencing the complexity and variety of potential chemical elements and compounds. You could imagine a universe with a completely different periodic table, or one where the conditions make complex chemistry fundamentally impossible. The cosmological constant, which is thought to drive the accelerated expansion of our universe, could also differ dramatically. In some universes, a far greater cosmological constant might cause expansion so rapid that matter never clumps together to form galaxies and stars, leaving a cold, empty cosmos. Conversely, a smaller cosmological constant could cause a universe to eventually collapse back on itself in a big crunch, perhaps initiating endless cycles of cosmic expansion and contraction. It's also conceivable that other universes feature variations in the laws of quantum mechanics themselves, altering the principles that dictate particle behavior. This could give rise to universes where concepts like uncertainty, superposition, and entanglement operate in entirely different ways, potentially unlocking new forms of computation or communication that are beyond the limits of our own observable reality. The sheer number of worlds where advanced civilizations might arise grows exponentially, fueling speculation about the nature and diversity of life throughout the cosmos. Our current technology confines our view to the observable universe, a sphere of space with Earth at its center, defined by the distance light has traveled since the Big Bang. Beyond this boundary lies the unobservable universe, an immense region whose light has not yet had time to reach our instruments. Still, the laws of physics as you and I know them do not preclude the existence of planets, galaxies, and even life in these faraway realms.
If the conditions in these unseen regions mirror those that allowed life to flourish on Earth, it is entirely reasonable to assume that advanced societies could have emerged and evolved there. They might have developed technologies and perspectives that are far beyond our current comprehension. The concept of the multiverse further amplifies this possibility, suggesting that in some of the countless other universes, the conditions for intelligent life could be even more favorable than in our own. Such civilizations might have achieved a mastery of their cosmos, possibly even developing universal methods of travel or communication.
The search for extraterrestrial intelligence, or SETI, has not yet found definitive proof of advanced civilizations within our observable sphere. This lack of contact, however, hardly disproves their existence beyond the reach of our current technology. The immense distances and our own technological limitations present formidable obstacles to detecting such civilizations. Any signal, whether electromagnetic or of some other hypothetical kind, would need to cross vast cosmic voids over millions or even billions of years, demanding detection capabilities that are far more advanced than what we currently possess. The prospect of advanced civilizations thriving in the unobservable cosmos does more than just inspire scientific investigation. It also invites deep philosophical and ethical reflection on humanity's place in the universe. It encourages you to think about the nature of these potential societies, their cultures, technologies, and philosophies, and to consider how they might have navigated the very same challenges that we are facing today, or will confront in the future. Humanity's deep-seated curiosity has always propelled us to explore the cosmos, pushing us to comprehend our place among cosmic neighbors, and in doing so, to better understand ourselves. This exploration naturally leads to imagining the capabilities of civilizations far beyond our observable universe, which provides a compelling exercise in speculative science and reveals the very boundaries of our current knowledge.
Should such civilizations exist, Their technological evolution would likely grant them methods of observation and communication that we can only dream of. Imagine, for instance, theoretical telescopes so powerful they dwarf any instrument we possess, capable of warping the very fabric of space-time. This would not only grant them an unparalleled view of distant galaxies, but could also circumvent the light speed limitation that confines our own observations, effectively allowing them to witness cosmic events in real time, no matter how many billions of light-years away they occur.
Another fascinating possibility lies in communication through quantum entanglement, a principle where linked particles mirror each other's states instantly, regardless of the distance separating them. A sufficiently advanced society could exploit this phenomenon to create a communication system that transmits information across immense cosmic expanses without any time delay. A network like this would be free from the constraints of light-speed travel for signals, enabling a civilization to stay connected and unified across intergalactic or even universal distances. You also have to consider wormholes, theoretical shortcuts through space-time that could drastically reduce interstellar travel times, as another technology such civilizations might have mastered. If the challenges of creating and stabilizing these passages, a possibility hinted at by certain solutions to Einstein's general theory of relativity, were overcome, they could serve as conduits for instantaneous travel or communication. This would transform the cosmos from an impossibly vast expanse into a navigable domain. The very structure of our universe, as outlined by Albert Einstein's general theory of relativity, remains a wellspring of deep-seated puzzles and speculation. Even though our current theories have illuminated much about the cosmos, there are undoubtedly facets of space-time that are still far beyond our ability to comprehend. Unraveling these enigmas promises to fundamentally reshape our understanding of the universe and the physical laws that dictate its behavior.
Among these great unknowns is the true nature of dark energy and the full extent of its effect on space-time. We can see its impact in the accelerating expansion of the universe, but its core properties and the way it operates are still a complete mystery. It's conceivable that dark energy holds the key to manipulating space-time in ways we can't yet imagine, perhaps allowing for controlled expansion or contraction that could ultimately determine the fate of everything. Another profound puzzle awaits us at the Planck scale, the most minuscule level of reality, where our familiar concepts of space and time cease to apply. Physics theories propose that space-time at this infinitesimal level possesses a quantum, pixelated structure. Yet how this granular fabric generates the smooth continuum we perceive is an unsolved riddle. Discovering the secrets of this quantum realm could finally provide the long-sought bridge between general relativity and quantum mechanics, a unification that has been a primary objective for physicists for generations.
You must also consider the potential for higher dimensions, beyond the three of space and one of time that we perceive, which could unlock entirely new mysteries. Theories like string theory suggest these extra dimensions might conceal unknown forces, exotic particles, or even separate universes that influence our own through mechanisms we haven't yet detected. The questions of how these dimensions are curled up and hidden from us, and whether they could ever be accessed, remain some of the most exciting challenges in both theoretical and experimental physics.
Even the fundamental nature of time itself likely conceals secrets that would upend our current worldview. We experience time as a straight, forward-moving arrow, but future scientific breakthroughs could show us that it's far more complex. We might discover its potential for being stretched or compressed, its intricate connection to space in extreme environments like the edge of a black hole, or even find proof of phenomena that permit experiences or links outside of linear causality.
In addition, the ultimate destiny of the universe is a puzzle deeply woven into the nature of space-time itself. Our current models offer several speculative conclusions, including the heat death, the big crunch, or the big rip. But these are based on incomplete knowledge. The true finale could be something we haven't even conceived of, shaped by principles of space, time, and physics that are still waiting to be discovered. The sheer scale of the universe suggests the possibility of cosmic structures that are so enormous, intricate, or alien that their existence would force us to rethink our basic concepts of matter, space, and physical laws. These theoretical formations, which would lie beyond the 93 billion light-year diameter of our observable universe, mark the very edge of scientific inquiry and cosmic speculation. One such possibility involves the existence of what you might call superclusters or hyperclusters, cosmic arrangements so massive they make even the largest known structures seem small. Our observable universe already contains superclusters, which are immense collections of galaxies, but it is conceivable that an even more magnificent tier of cosmic organization exists just beyond our current horizon. Imagine hyperclusters stretching across hundreds of billions of light years. These structures contain not merely clusters, but entire networks of superclusters connected by a cosmic web of dark matter and energy, building a universal framework on a scale you can barely comprehend. Another speculative concept involves dark galaxies, which are amalgamations of dark matter almost entirely devoid of ordinary matter, rendering them practically undetectable with our current technologies. It's theorized that within these formations, distinct forms of dark chemistry, or perhaps even dark life, could exist, governed by physical laws that are profoundly different from those we know. These gravitational waves might unveil cataclysmic events from the dawn of time, such as the collisions of supermassive black holes, fundamental shifts in the vacuum state of the cosmos, or even the presence of cosmic strings. Similarly, neutrinos could be another source of unknown signals. As subatomic particles with nearly zero mass that barely interact with matter, they can journey across the entire universe from its most remote corners, carrying information from places you can't see. Catching ultra-high-energy neutrinos that originate from beyond the observable universe could give you vital clues about the conditions of the primordial cosmos. Such a discovery might expose the processes that led to the formation of the first structures, or even point toward a physics that operates beyond the standard model. Quantum fluctuations, which were stretched to cosmic scales during inflation, could also leave behind detectable traces as minute anomalies in the cosmic microwave background radiation, suggesting influences from phenomena outside our visible horizon, and perhaps even imprints from other universes. In multiverse theories, where distinct universes form like bubbles in space-time, it's proposed that hypothetical constructs such as axions, a candidate for dark matter, might produce signals you could detect. If these theoretical particles exist and can interact with our observable cosmos from beyond its edge, they could generate unique electromagnetic signatures under specific conditions. Finding such signals would not only confirm the existence of axions, but also provide a glimpse into the immense, unseen reality that surrounds us. Black holes, among the most baffling objects known to science, function as cosmic laboratories where you can push the limits of physics. Those that exist beyond the observable universe, in regions you cannot yet directly study, hold the promise of revealing some of the deepest cosmic secrets. One of the most significant of these secrets revolves around the nature of quantum gravity, as black holes create a conflict between general relativity and quantum mechanics relativity, which governs gravity on a large scale, and quantum mechanics, which rules the subatomic world. It is possible that black holes beyond our cosmic horizon exhibit behaviors that could help you resolve this fundamental problem of unification. The manner in which these distant black holes evaporate through Hawking radiation may offer insights into how gravity behaves at the quantum level, potentially paving the way for a comprehensive theory of quantum gravity. Another profound mystery they could solve relates to the birth and development of the early universe. Hypothetical primordial black holes, which might have formed from the collapse of dense regions shortly after the Big Bang, could be numerous in the regions beyond our sight. Observing these ancient objects could inform you about the state of the early cosmos, including how matter was distributed and what dark matter is truly made of. If these primordial black holes make up a large portion of dark matter, then detecting their signatures, like gravitational waves from their mergers, would illuminate the universe's dark sector. The information paradox, which questions what happens to information that falls into a black hole, also conceals fundamental truths about the universe. It's a puzzle. Does information get destroyed as classical physics implies, or is it somehow preserved as quantum mechanics demands? Resolving this paradox by observing black holes beyond our view could transform your understanding of entropy and the very structure of space-time. Furthermore, supermassive black holes in the unseen universe could shed light on galaxy formation under conditions vastly different from those you can observe. The interplay between these immense black holes and their surrounding dark matter halos, gas clouds, and star systems might offer unique perspectives on galactic dynamics across various cosmic eras. The discovery of black holes with properties not anticipated by current theories could unlock entirely new physics. This might include black holes existing in higher spatial dimensions, as some models predict, or those with unusual electrical charges or spins that defy our understanding of astrophysics, hinting at exotic particles or forces that appear only in the extreme environment of an event horizon. While black holes are well-established cosmic entities defined by a gravitational pull so strong that not even light can escape, the notion that they might act as bridges to distant parts of the universe, or even other dimensions, is grounded more in theory than in observation. Yet, this concept fuels the imagination and pushes you to explore the very limits of what you understand about the cosmos. Central to this idea is the theoretical object known as a wormhole. A wormhole is a hypothetical passage through the fabric of space-time that could connect two very distant locations or even link different universes. In certain theoretical models, the entrance to such a tunnel might look just like a black hole, complete with an event horizon, where the known laws of physics start to unravel. Physicists theorize that if wormholes are real, they could potentially allow for instantaneous travel across cosmic voids, or act as portals between separate universes in a multiverse. However, you face several profound challenges that keep this idea in the realm of speculation. For one, the stability of a wormhole is a major problem. Calculations suggest it would collapse too rapidly for anything to pass through unless propped open by a type of exotic matter with negative energy density, something that has never been discovered. Moreover, the concept of traveling through a black hole to another place confronts you with the singularity at its heart, a point of infinite density where, according to current theories, the laws of physics as you know them cease to exist. A significant puzzle that confronts modern physics is how any matter or information could survive traversing a singularity. To find answers, we look to the early universe, the era just after the Big Bang, which contains vital clues about the nature of the cosmos, well beyond the limits of what you can currently observe. We can glimpse this primordial era through the cosmic microwave background, or CMB, which is essentially a photograph of the universe when it was merely 380,000 years old. By analyzing this relic radiation, You gain a window into the conditions of that time and hints about the immense cosmos beyond our reach. A critical piece of evidence from the CMB is its astonishing uniformity across the entire sky.
This incredible consistency in temperature exists even between regions so far apart they could not have exchanged information since the Big Bang, a state known as being causally disconnected. This puzzle led to the formulation of inflationary theory, the idea that the universe experienced a period of explosive expansion almost immediately after its creation. This process would have smoothed out inconsistencies and suggests that areas of space now outside your view were once linked to our own, implying a fundamental uniformity across the entire cosmos.
Another crucial piece of the puzzle comes from quantum fluctuations that occurred during this inflationary period. These microscopic variations in density were stretched by the rapid expansion, eventually growing into the seeds for every structure you see today, from galaxies and their clusters to the immense cosmic web. The patterns of these fluctuations suggest that similar cosmic structures likely formed throughout the universe, including in realms you cannot yet see, and they provide the basis for our models of cosmic inflation.
The universe's infancy also illuminates the nature of dark matter and dark energy, two of its most enigmatic components. The influence of dark matter on the formation of galaxies, as seen in the CMB, points to its properties being consistent across the cosmos. Likewise, the accelerated expansion driven by dark energy appears to be a universal phenomenon, suggesting that the dynamics you observe within your cosmic horizon are at play everywhere.
Further evidence arises from studying the primordial elements created in the first few minutes after the Big Bang, a process called nucleosynthesis. The observed abundances of helium and lithium match theoretical predictions perfectly, reinforcing the idea that the same physical laws operate everywhere. Additionally, gravitational waves, ripples in space-time from the universe's earliest moments, could carry information from the unobservable cosmos, potentially revealing structures and phenomena completely beyond your current comprehension.
In the initial moments following the Big Bang, the universe experienced an explosive expansion phase called cosmic inflation. This phenomenal growth stretched space-time, eliminating initial irregularities and producing the large-scale uniformity you observe today. This inflationary epoch was foundational, as it established the structure for the entire cosmos, including the parts beyond your observational reach. It strongly suggests that all regions of the universe, both seen and unseen, share a common origin, and were shaped by the same dramatic expansion.